Imagine a machine where metal blades spin faster than the speed of sound. Temperatures soar hotter than molten lava, and the margin for error is measured in fractions of a millimeter. This is not science fiction. This is the everyday life of a jet engine. But how is it possible to build something so powerful, so precise, and so resilient that it can carry hundreds of people across continents, all while withstanding some of the most extreme conditions engineered by humans? That's the story of how jet engines are built to endure the unimaginable. Let's step inside the world where heat, pressure, and speed reach their limits, and where failure is simply not an option. First, consider the environment inside a jet engine. Air rushes in at hundreds of miles per hour, is compressed up to 40 times its original pressure, mixed with fuel, and then ignited. The result? Temperatures in the hottest parts of the engine. The combustion chamber and turbine can reach nearly 1,700 degrees Celsius, well above the melting point of most metals. Yet the blades and walls don't melt. Why? The secret lies in the materials and the engineering behind them. The main components of jet engines are crafted from superalloys, special blends of metals like nickel, cobalt, and chromium. These metals are chosen because they don't just tolerate high temperatures. They maintain their strength and resist corrosion even at extreme heat. Superalloys are the unsung heroes of the engine world. But even the best metal will melt or deform if it gets too hot. To solve this, engineers developed a process called single crystal growth. Instead of casting turbine blades as a solid mass of randomly arranged crystals, they grow them as a single, continuous crystal. No grain boundaries, no weak points. This method lets blades operate at higher temperatures without failing. But materials alone aren't enough. The design is just as critical. Let's talk about cooling, a paradox in the heart of the engine. To keep turbine blades from melting, they're built with tiny, intricate channels inside. Cold air, bled off from earlier stages in the engine, is routed through these passages. As the air snakes through, it keeps the metal just cool enough to survive, even as the outside is blasted by roaring hot gases. This technique is known as internal air cooling, and it's a masterpiece of modern engineering. Another trick? Thermal barrier coatings. Imagine painting your entire house with heat-proof paint that keeps the summer sun out. In jet engines, the most heat-exposed parts are sprayed with a thin ceramic layer, a barrier that deflects some of the blistering heat away from the metal underneath. This adds precious degrees of safety and allows the engine to run even hotter, pushing it to greater efficiency. But there's more to surviving extremes than just heat. The engine has to cope with enormous centrifugal forces. As blades spin at over 10,000 revolutions per minute, each blade can experience forces equivalent to several tons trying to rip it from its mountings. Here, every gram matters. Removing even a small scrape of metal from a blade can mean the difference between smooth operation and catastrophic failure. To manage this, engineers use advanced manufacturing techniques, precision forging, computer-controlled machining, even 3D printing for some components. Tolerances are measured in microns. Every blade is weighed, balanced, and fitted to perfection, sometimes even matched in sets, so their combined effect on rotation is minimized. Of course, a jet engine doesn't operate in a sterile, controlled laboratory. At cruising altitude, an engine faces frigid outside temperatures, sometimes dropping to -60 degrees Celsius, while its interior blazes at over 1,000 degrees hotter. Early in the morning, at high altitude, as a plane crosses continents, metal must expand and contract, over and over again, without fatigue or cracking. Engineers test and retest for this, cycling components through endless rounds of rapid heating and cooling, what's called thermal fatigue testing, so the finished parts are ready for real-world extremes. Then there's pressure. As the air is squeezed by the compressor stages, each section of the engine must withstand a pressure difference strong enough to shatter ordinary casings. This is why engine cases, rotors, and stators are made from extra tough, hoop-strengthened alloys. Some parts are spun on super-strong machines, stretching and hardening the metal grain to resist bursting. Safety here is absolutely paramount. A single failure could mean disaster, but jet engines also have to resist invisible threats from within: vibrations. Each turbine blade, when spinning, is like a tuning fork. The right or wrong vibration can amplify until it snaps. So engineers build dampers, design shapes that break up resonance patterns, and use sensors to watch for signs of trouble, all while the engine is humming along at full throttle. Sometimes tiny add-ons called Snubbers are added to blades, acting like little shock absorbers to dampen dangerous vibrations before they build up. All of these challenges, heat, pressure, vibration, fatigue, are overcome thanks to a deep understanding of physics and relentless trial and error. But keeping a jet engine running for thousands of hours in the real world requires more than just clever design. That's where maintenance comes in. Every commercial jet engine is tracked from birth to retirement. Sensors gather data on temperature, vibration, oil pressure, every flight. When a part wears out, it's replaced not after something breaks, but before. Blades are scanned for microscopic cracks using X-rays and ultrasonic waves. If one is found with even a hint of damage, it's repaired or swapped out. Sometimes entire engines are cycled out for deep overhaul, stripped down, and rebuilt for another life in the sky. This meticulous monitoring is why modern jet engines are astoundingly reliable. Decades ago, jet engines were overhauled every few hundred hours. Today, some can run for tens of thousands without a major teardown. This constant cycle of build, test, operate, maintain, and learn is the thread that runs through every great advance in jet engine resilience. There's also innovation in the air itself. Scientists and engineers are always seeking new ways to make engines tougher, lighter, and more efficient. Recent advances include ceramic matrix composites, which are even lighter and more heat-resistant than the best metal alloys. Some new engines use 3D printed metal parts, with shapes so complex they could never be carved or cast traditionally. These structures might look odd or intricate, but they help manage heat flow, reduce weight, and increase efficiency, all while shrugging off the same extremes that would destroy ordinary parts. It's impossible to ignore how the demands placed on jet engines reflect our constant quest to travel further, faster, and more safely. Whenever a new engine comes online, its designers aren't just thinking about speed or power. They're thinking about thousands of flights over years, through swirling storms, volcanic ash, hail, and icy altitudes. They're thinking about passengers asleep over the Atlantic, not knowing that beneath the wing, a masterpiece of engineering is relentlessly battling the elements, keeping everyone aloft. Consider this. A single wide-body jet engine is so carefully balanced that its spinning core, rotating at tens of thousands of RPM, generates almost no vibration detectable by passengers. Each movement, each pulse, is absorbed and redirected by decades of experience made metal. This is not brute strength. It's harmony engineered from chaos. And every advance has a ripple effect. Stronger, lighter jet engines mean less fuel burned, fewer emissions, longer ranges, and lower costs. They also open the door to even more ambitious projects. Hypersonic planes, space planes, and perhaps someday engines that operate seamlessly between atmosphere and orbit. It's almost poetic how the boundaries of human invention are continually redrawn by people who study what looks like the edge of possibility and decide to build there anyway. So the next time you sit in a jet, gazing out at the engine silently working just outside your window, remember, beneath its smooth shell is a symphony of extremes. Unbearable heat, bone-chilling cold, unthinkable speed, impossible pressure, all funneled into reliable thrust by a marriage of super materials, mind-bending engineering, and relentless testing. That engine is a monument to our need to move, to explore, and to master the unforgiving elements, soaring from runway to sky safely every day. And that is how jet engines are built, not just to work, but to survive in a world where conditions are always just one step away from the impossible. To keep turbine blades from melting, they're built with tiny, intricate channels inside. Cold air, bled off from earlier stages in the engine, is routed through these passages. As the air snakes through, it keeps the metal just cool enough to survive, even as the outside is blasted by roaring hot gases. This technique is known as internal air cooling, and it's a masterpiece of modern engineering. But materials alone aren't enough. The design is just as critical. The engine has to cope with enormous centrifugal forces. As blades spin at over 10,000 revolutions per minute, each blade can experience forces equivalent to several tons trying to rip it from its mountings. Here, every gram matters. Removing even a small scrape of metal from a blade can mean the difference between smooth operation and catastrophic failure. To manage this, engineers use advanced manufacturing techniques, precision forging, computer-controlled machining, even 3D printing for some components. Tolerances are measured in microns. Every blade is weighed, balanced, and fitted to perfection, sometimes even matched in sets, so their combined effect on rotation is minimized. Engineers test and retest for this, cycling components through endless rounds of rapid heating and cooling, what's called thermal fatigue testing, so the finished parts are ready for real-world extremes. Metal must expand and contract over and over again without fatigue or cracking. As the air is squeezed by the compressor stages, each section of the engine must withstand a pressure difference strong enough to shatter ordinary casings. Some parts are spun on super strong machines, stretching and hardening the metal grain to resist bursting. Safety here is absolutely paramount. A single failure could mean disaster. But jet engines also have to resist invisible threats from within. Vibrations. Sometimes tiny add-ons called Snubbers are added to blades, acting like little shock absorbers to dampen dangerous vibrations before they build up. All of these challenges, heat, pressure, vibration, fatigue, are overcome thanks to a deep understanding of physics and relentless trial and error. But keeping a jet engine running for thousands of hours in the real world requires more than just clever design. That's where maintenance comes in. Decades ago, jet engines were overhauled every few hundred hours. Today, some can run for tens of thousands without a major teardown.